Now we're going to look at threats to internal validity. In the previous lecture we looked at threats to external validity. Internal validity, I apologize, this is a bit long, but this is a really big topic. This is really the meat of econometrics. This is basically every problem is a systematic way of diagnosing problems in statistical studies. So let's remind ourselves, what is internal validity? If the statistical inference about the causal effects are valid for the population being studied, then we have an internally valid study. In other words, do the results make sense for the participants in a laboratory experiment if we want to run a laboratory experiment? Do the results make sense for elementary school students if we're doing our student CT ratio and test score example? Are the results valid at all? So we have 5 different threats to internal validity in a regression in OLS. In this section we will cover omitted variable bias, threat number 1, misspecification of the functional form of the regression function, that's number 2. We have imprecise measurement of the independent variables or errors in variables. This is also essentially measurement error. We have sample selection and simultaneous causality. And all of these imply that the expected value of the error term conditional on x does not equal 0. In other words, they imply correlation between u and x does not equal 0, in which case OLS is biased. So all of these essentially violate OLS assumption number 1. So let's look at these in turn. Number 1, omitted variable bias. We've seen this many times in our lectures, and we've talked about solutions for this, but let's go over this again real quick. Solutions when omitted variables are present. If you have adequate data, you can just include the variable causing omitted variable bias. So in our test score and student-teacher ratio example, the big one was % English learners, right? So here we have the base regression where U contains % English learners, right? % ESL. So U is a function of that, and we know that % ESL satisfies the 2 conditions for omitted variable bias. Go look that up if you don't know those 2 conditions. And so we know that in this specification, we've seen this, that the correlation between U, which is a function of % ESL, and I'm going to run out of room here, STR, we know that this does not equal 0. We know there's some correlation there, so assumption number 1 is violated in regression 1. So we prefer regression 2, where we include % ESL. Right. Okay. So one solution is if you have adequate data, you just add the additional variable to the model, removing the omitted variable bias. However, adding variables has trade-offs. The benefits of adding omitted variables include reducing bias in coefficients, so that's what we've talked about, but the costs are that the additional variables tend to reduce statistical significance of the existing coefficients. In other words, it increases your variance of your beta hats. It'll increase the variance of the beta 1, and so we might get statistically insignificant results. So we have to balance these 2 things. So how to decide whether or not to include additional variables? We want to be specific about the coefficient or coefficients of interest. Be clear about the effect you're looking for. We care about student-teacher ratios. Use reasoning and argument to identify the most important sources of omitted variable bias. So there's no right or wrong answers here. This is all based on argument at this point. This is where I usually describe econometrics as becoming an art form. You want to identify your base regression. So we've done this in the previous examples. We have test scores on student-teacher ratios as our base regression. Think hard about what could affect test scores that is important and could bias the coefficient on student-teacher ratio. In other words, think hard about what is left out of this regression. Develop a list of questionable variables that you think are important and that you should test by including them if you have data on them. And then test whether the questionable variables in the previous step have non-zero coefficients. So test to see when you add them, do they have non-zero coefficients in the model? And then also test if the coefficient on student-teacher ratio is affected by the addition of those, the inclusion of those other variables. You want to present an accurate summary of all your regression results in a table, and then identify potential issues, and then make a case for why your preferred specification is the one. Well, you want to argue for why you've chosen your preferred specification. Omitted variable bias solutions when you don't have additional data. So this is where you go in graduate school econometrics. You will learn about things called instrumental variables. We'll have panel data, which is data that has a timed component and a cross-sectional component. And we can include things like fixed effects or random effects to control for all these omitted variables. And then ultimately we would ideally have random sampling. So we're not going to cover all these things in this class, but if you want to go on in econometrics, that's where you'll go. Number 2, threat to internal validity, wrong functional form or misspecification. So we've talked a bit about this in lecture or module 7 when we were doing the linear function versus the quadratic. This is what we're talking about here. It arises if the functional form is incorrect. It may have a good estimate at particular values of x but bad elsewhere. If interaction term is incorrectly omitted, then causal effects will be biased. So what is that one saying? That's an interesting one. Let's relate this one to omitted variable bias, right? So suppose y is a function of x1, but now suppose u, well, we know that u contains, I'm writing contains as u is a function of, let's say x2 and x1 times x2. So u contains both x2 and the interaction of x1 and x2. And the problem is if this bit is an important predictor of y, then it's an omitted variable. So we're back to our omitted variable bias problem. So this is how the interaction model is just a different case of omitted variable bias. So x2 might be an omitted variable by itself causing bias in the coefficient beta 1, but x1 times x2 might also be an omitted variable causing bias. Solutions, we want to, for continuous dependent variables, we want to use appropriate nonlinear specifications in x. We've talked about this, having squared or cubic terms of x. We haven't gotten to this where we have discrete dependent variables or binary dependent variable. We would need different methods called the logit and probit. Threat number 3, errors in variables bias or measurement error. So this is essentially when x is not measured correctly. And so far we've assumed that x is measured without error. It's correct. But often this is not the case. We might have data entry errors. In other words, there might be somebody sitting at a computer putting data into a spreadsheet. If that person has fat thumbs, this is kind of the joke that everyone is going to do this regardless of your thumb size, that you're not going to be perfect, right? You're going to add an extra 0 here or exchange a 7 for a 6 or something like that. So there's measurement error. There's data entry problems. There's recollection error in surveys. Maybe somebody surveyed you, they asked you, what's your income? Well, I don't know exactly what my income is at the moment. My annual income, I just don't know off the top of my head. And people lie on surveys. What is your income? Maybe I'm going to inflate it a little bit. How often do you drink and drive? Oh, never, of course. You might be asking ambiguous questions on a survey. So these are the types of things we should be concerned about as data analysts. So measurement error in practice. So suppose we have this is our baseline model here. This is the correct model in the sense that the 3 least squares assumptions hold, especially the first, that the error term is uncorrelated with x. And let x by itself be the unmeasured true value of x. So this is the real value of x, and then let x wiggle, this thing here, be the observed or imprecisely measured value, measured x. Then we can, what we were actually estimating is the following equation. So we want to estimate 1, but in fact we're estimating 2, where we regress y on x wiggle, plus this error term u wiggle, where u wiggle is equal to this bit here. When this bit is defined as the additional measurement error, so the difference between the true value of x and the mismeasured value of x times the beta 1 coefficient, but that's unfortunately contained in our error term, so it's unobserved, causing omitted variable bias. And in order for, this should be beta hat 1, to be unbiased, we need the expected value of this, our real error term, u wiggle, to be uncorrelated with the mismeasured value of x, x wiggle. So we need this to hold. But this doesn't usually hold in practice because the mismeasured value of x is usually correlated with the measurement error, x minus the true value minus the mismeasured value, which leads to a bias estimate of beta hat 1. So this is also the same as omitted variable bias, where the omitted variable in this case is actually just the mismeasured value of x, the difference between the true value and the imprecisely measured value. If we could control for that, we would get an unbiased estimate of beta 1, but we can't. And so we get a biased estimate of beta 1. We have something called classical measurement error. And so suppose x wiggle is equal to the true value of x plus w, where w is a purely random component, mean 0 and variance sigma squared w. So this is the case where the measurement error is uncorrelated with x wiggle. The problem is that even if it's uncorrelated with the mismeasured value of x, then we still get a bias coefficient of beta 1, and I'll show you how this happens in practice. Because the measurement error is random, it will be uncorrelated with xi, the true value of x, and ui, or correlation wx equals 0 and correlation wu equals 0. With some algebra, we can show that beta 1 hat beta 1 hat in the model where we're regressing y on x wiggle, u wiggle, beta 1 hat converges in probability to sigma squared x over sigma squared x plus sigma squared w times the population value of beta 1. If there's no measurement error, this sigma squared w term cancels out, and we get the variance of x over the variance of x, which turns into 1. So those cancel out, and beta hat 1 converges in probability to the population value beta 1. When there is measurement error, though, the variance of w, the variance of the measurement error, is some positive value, and so the denominator here, is larger than the numerator, meaning that the right-hand side is less than the left-hand side of this equation. So what this is saying, in the presence of classical measurement error, beta hat 1 converges in probability to something less than beta 1, the population value. Therefore, if the measurement error is purely random, our estimate of beta hat 1 is inconsistent, and then it will also be biased. Further, because this is less than 1, beta hat 1 will be biased towards 0, even in large samples. If the measurement error is so large that it overpowers the variation in x, then beta hat 1 converges to 0. And if the measurement error is 0, then beta hat 1 converges to beta 1. What if there's measurement error in y, the dependent variable? In that case, we're a little better off. It increases the variance of the beta hat estimates, but does not bias them. And so we can see this as an example. Example here. Suppose measured yi is y wiggle, equal to the true value yi plus some random error component wi. Then the regression model estimates y wiggle, our data, as a function of x plus v, where v is equal to the random error component plus the real error component from our regression model. If wi is random, then wi and xi are uncorrelated because they are independent, so the expected value of wi xi is equal to 0, meaning that the expected value of the entire error term conditional on the x term is equal to 0. So we are in good terms, all good in terms of bias. We've satisfied OLS assumption number 1. Therefore, correlation between our error term v, that should not be in a line, that should be a comma, and x equals 0. And so we have no bias, but remember the variance of vi is greater than the variance of ui, so the variance of beta hat 1 is larger than without measurement error. And so we're going to fail to reject our null hypotheses more often in the presence of measurement error in y. Solutions to the measurement error problem: get better data, develop a method to address or model the measurement error. Could be a lot of checking data by hand. I have an example of, could be regressing satellite images on water use. Ask me about that in office hours if you're curious. This is one way I've addressed measurement error in my work. And again, instrumental variables regression, so that's something you would learn about in a master's course. Number 4, sample selection bias. This is remember we're in threats to internal validity number 4. And so far we've assumed random sampling of the population. But sometimes this assumption doesn't hold because the sample in effect selects itself. We have sample selection bias occurs when selection process is influencing the availability of data, and that process is related to the dependent variable. So let's think of some examples. Suppose we want to test the effect of a particular drug on the population. Random sampling would mean we would go out and randomly sample individuals from the population, and that means we are equally likely to get any person from the population. They could be healthy or sick, they could be old or young, they could be male or female, they could be wealthy or poor, because they could have alternative habits that impact the effectiveness of the drug. These things matter. And what if we instead seek out participants from the population? You might get these emails or see flyers that say, participate in this study. Who's going to participate? Well, if it's a paying study, it's the people that need the money. And these people could be sick. They might want the drug to see if it can help them. And importantly, the selection process of the participants is not random, meaning that we are, in this case, we're more likely to get sick people. We might be more likely to get young people. We might be more likely to get poor people. And the effect of the drug on that segment of the population might be different from the effect of the drug on the healthy, the old, and the wealthy. So that's what we mean by sample selection bias. The solutions to the sample selection bias problem are as follows. So we could reinterpret our coefficients. Example number 2, we had returns on education. Often studies that look at education effect on the effect of education on income look at only the employed population. And this biases the coefficients upwards because we are leaving out the college grads that are unemployed, or this calls for reinterpretation of the coefficients. The effect of education on income, we could think of this not as the effect of education on income, but we would think of it as the effect of education on income for the employed. So we're just reinterpreting the coefficients and then they're correct. We could run a randomized controlled trial, but those are expensive to do. We would have to go collect our own data, get a grant to do so. Typically that's not an option, and so we oftentimes we end up relying on solution number 1. We can construct a model of sample selection and estimate the model and then try to figure out how bad the sample selection is and account for it. This one is done in practice, but it's a lot harder than just reinterpreting the coefficients. And then Threat number 5, simultaneous causality. So far we've assumed that X causes Y only, but what if Y also causes X? Let's look at an example. Supply and demand. We know that the price affects the quantity demanded, but quantity demanded, this should be affects, demanded also affects the price, which in turn affects the quantity supplied. Write down a demand function. We have quantity demanded as a function of price, the supply function, quantity supplied as a function of price. When we have data on quantity, which one do we have? We don't know, right? So if we just collect data, we don't know if we have data on the quantity demanded or the quantity supplied. And in practice, we get equilibrium data. We get the quantity that turned out to clear in the market. And so we have both. So when we're estimating this model, what are we getting? Suppose we estimated the quantity, so we're assuming we have QS and we regress it on price. So this should be a supply function that's upward sloping, right? QS. But what happens if we estimate this model and beta 1 is negative? What does this imply? This implies that we've estimated some downward sloping function that's actually not a demand function, but it's something similar to a demand function. So again, in graduate school, you'll learn how to estimate supply and demand functions in the presence of simultaneity like this. Another example, the effect of peers on educational outcomes. What if we want to figure out how do my peers affect my grades? So we regress my test score, this I should be over here, my test score on person I on my peers' test scores. So people, not I, people in my peer group. Clearly my peers influence me and I influence my peers. So the question here is the effect going this way or is the effect going this way? What if I'm kind of the leader in the group? I'm the smartest in the group, and so maybe I'm more of an influence on my peers than they are on me. When this happens, beta 1 picks up both effects, not just one direction of causality, so you're going to get this sort of combined effect estimate. Mathematically, we have the causal effect of x on y, yi equals beta 0 plus beta 1 xi plus ui. The causal effect of y on x, where xi is equal to, these are called gammas, gamma 0 plus gamma 1 yi. So now we have y on the right-hand side and x on the left-hand side. How does this work? Okay, if we have a large ui, a large residual for person I, this means that we have a large yi, right? So the ui is causing larger ui's, larger residuals mean larger yi's, and by equation 2 here, a larger yi causes a larger xi if gamma 1 is positive, and therefore there's correlation between the u and the x in the first model, and that means that we're violating assumption number 1 in the first model. Expected value of ui conditional on xi does not equal 0, meaning the correlation between ui and xi does not equal 0, and so we're back to the omitted variable bias problem, or we violated assumption number 1, and therefore beta 1 hat is inconsistent and biased, and so would be gamma 1. This slide just kind of restates what we've said. If there's a particularly smart student with a relatively high yi test score, then the ui will also be relatively large. And looking at the second equation, if that student's test score is really large, then xi will be large so long as gamma is greater than 0, and therefore yi is affecting x and x is affecting y. This also means that u is correlated with x, violating assumption number 1. So solutions to simultaneity. Again, a randomized controlled experiment. Since xi would be chosen at random, there's no feedback from the outcome variable to yi. And we could develop an estimated complete model of both directions of causality. This is difficult, but it can be done. We can also use something called, again, instrumental variables, and we would get to that in a graduate course. So that's the threats to internal validity. We've also seen threats to external validity. It's a lot of information. In summary, these 5 threats that we just talked about, if we go all the way back to the beginning of this, where we listed the 5 threats to, here we are, 5 threats. If you systematically go through your regression models or your somebody else's regression models, and you think about each of these in turn, then you can, and you feel pretty good about them, then you have a pretty good regression output. And so this is a nice framework for thinking about evaluating your own regressions and other people's regressions.